Module 27, Lecture A, CV Splitters. By the end of this lecture, you will be able to use Scikit-Learn cross-validation utilities to estimate model performance, choose appropriate splitters for classification, regression, grouped, and time-ordered data, and inspect fold assignments and predictions produced by cross-validation. Cross-validation utilities. Holdout evaluation. Holdout evaluation in Scikit-Learn estimates how well a model performs on new data by splitting a dataset into separate training and testing parts. The train test split tool randomly separates features and labels while keeping them correctly matched. Because the test data is not used during training, this method helps reveal overfitting and gives a more realistic view of how the model may generalize. Holdout evaluation is a simple, fast way to estimate model performance, especially when first exploring a dataset or comparing models. Its reliability depends on choosing an appropriate test set size. Too small can give unstable results, while too large can leave too little data for training. The best split depends on the dataset and the cost of errors, so sensitive or rare case data needs extra care. Overall, holdout evaluation is useful as a starting point, but more thorough validation may be needed. Holdout evaluation depends on how the data is split, so randomness and reproducibility matter. Using a fixed random setting in Scikit-Learn gives consistent training and test sets, which helps with debugging and fair model comparison. For classification, especially with imbalanced data, the split should preserve class proportions to avoid misleading performance estimates. Overall, holdout evaluation gives a quick snapshot of model performance before using more thorough methods like cross-validation. Python code. Holdout evaluation. This script shows holdout evaluation by splitting the data before training, then measuring the model's performance on examples it has not seen. We import the main Scikit-Learn tools needed to build a simple classification workflow. These include the breast cancer dataset loader, logistic regression model, accuracy scoring, train test splitting, pipeline creation, and standard scaling. Together, these tools let us load the data, standardize the features, split the dataset, train the model, and evaluate its performance. We load Scikit-Learn's built-in breast cancer dataset for a classification task. The input features come from the dataset's data attribute, and the labels to predict come from its target attribute. This prepares the data for later processing and model training. The code verifies that the feature data and target labels have the same number of entries, so each feature set matches one label. If they do not align, it raises an error to prevent incorrect training or evaluation. We split the dataset into training and testing sets using the train test split function with the features and target as inputs. 25% of the data is kept for testing. Stratification preserves the target class distribution, and a fixed random state makes the split reproducible. The result is separate training and testing features and labels. A Scikit-Learn pipeline combines standard scaling with logistic regression. Scaling standardizes the features, so the model is not affected by differences in feature size, which is important for logistic regression. The model is set to allow up to 1,000 iterations, with a fixed random state to make training results reproducible. The logistic regression model is trained by fitting it to the training set's features and labels. During this process, the model adjusts its parameters to reduce the gap between its predictions and the actual labels, allowing it to learn patterns from the data. To evaluate the model, we use the held-out test data to generate predictions and compare them with the true labels. The accuracy score from Scikit-Learn measures the share of correct predictions. This test accuracy shows how well the model performs on new, unseen data. To check how well the model fits the training data, we calculate its training accuracy using the model score method with the training features and labels. This result can then be compared with test accuracy to help identify possible overfitting or underfitting. The code reports key details about a machine learning run, the scikit-learn version, the number of training and test examples, and the model's accuracy on both sets. These outputs help confirm the setup, show the dataset split, and compare performance on trained data versus unseen data to assess generalization. This script shows a holdout evaluation on a breast cancer dataset. It splits the data into stratified training and test sets, scales only the training data, and trains a logistic regression model. The untouched test set is then used to estimate how well the model generalizes. By reporting the data split sizes and both training and test accuracy, the script helps reveal possible overfitting or underfitting. Cross-validation scores. Cross-validation estimates how well a model will perform on new data by repeatedly training and testing it on different splits of the dataset. Each split produces a score, giving a more reliable picture than a single test set. Consistent scores suggest the model generalizes well, while widely varying scores may mean its performance depends heavily on the specific data split. Cross-validation helps show whether a model's performance is truly reliable or just the result of a lucky train-test split. By testing across different data subsets, it reveals both the typical score and how stable that score is. A model with slightly lower but consistent results may be more trustworthy than one with a higher average score that varies widely. When using Scikit-Learn cross-validation, choose a scoring metric that matches your goal. Use error-based metrics for regression and accuracy or imbalance-aware measures for classification. Treat cross-validation scores as estimates that support model comparison, and interpret them alongside good data preparation and careful analysis. Python code. Cross-validation scores. Cross-validation estimates how well a model performs by producing an accuracy score for each fold. These scores are then summarized to show the model's typical performance and how stable that performance is. We import the main tools needed to build and evaluate a classification model. NumPy supports numerical work, while Scikit-Learn provides the breast cancer dataset, logistic regression, StratifiedKFold cross-validation, performance scoring, pipelines, and feature standardization. Together, these tools let us scale the data, train a logistic regression model, and evaluate it reliably while preserving class balance across folds. We load Scikit-Learn's built-in breast cancer dataset for a classification task. The input features are stored separately from the target labels, making the data ready for analysis and model training. The code verifies that the feature data and labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error. This check helps prevent training or evaluation problems caused by mismatched data. We build a simple machine learning pipeline that first standardizes the features, then trains a logistic regression classifier. Standardizing removes the mean and scales features to unit variance, which helps logistic regression work reliably. The model is given enough iterations to converge, and a fixed random state supports reproducible results. Using a pipeline also ensures that scaling is applied separately within each cross-validation fold. We use StratifiedKFold cross-validation to evaluate the model while keeping the class balance consistent in each fold. The data is split into 5 shuffled, reproducible parts, and the model is tested across these folds. The resulting accuracy scores show how well it performs on different subsets of the dataset. The code rounds the cross-validation scores to 3 decimal places so they are easier to read. It then reports the average score as a single measure of model accuracy, and the standard deviation to show how much performance varies across folds. The output summarizes a cross-validation run by first showing the Scikit-Learn version for reproducibility. It then reports the rounded accuracy scores for each fold, followed by the mean accuracy as an overall performance measure. The standard deviation shows how much the scores vary across folds, indicating how consistent the model is. This script tests a logistic regression model on the breast cancer dataset using 5-fold stratified cross-validation. It scales the features separately within each fold, then reports the Scikit-Learn version, the accuracy for each fold, and the mean and standard deviation. These results show both the model's typical accuracy and how consistent it is across different data splits. Cross-validate predictions. Cross-validated predictions estimate how a model performs on unseen data by training on some folds and predicting on the held-out fold. This gives each case an out-of-sample prediction, helping reveal realistic model behavior, such as identifying high-risk patients in medical screening. Scikit-Learn can automate the splitting, training, and collection of these predictions for easier case-level analysis. Cross-validated predictions help evaluate a model by showing which individual cases it gets right or wrong, not just an overall score. Because each prediction is made by a model trained without that case, the comparison with the actual result is fairer and more useful for diagnosing errors. This can reveal patterns such as bias across groups or weaker reliability for certain types of items. Cross-validated predictions come from several models trained on different subsets of the data, so they are not the same as predictions from one final model trained on the full dataset. They are best used during development to evaluate performance and inspect individual cases, such as spotting misassigned credit risk categories or studying housing patterns. The final model is typically trained on all available data, while cross-validated predictions help show how it may perform on new data. Python code cross-validate predictions. Use cross-validated predictions to evaluate iris samples that were held out during training. Each prediction is made by a model trained on a different fold, giving a fair comparison between the predicted and true labels. We import key Python libraries for a simple machine learning workflow, NumPy and Pandas for data handling, and Scikit-Learn for modeling and evaluation. Using Scikit-Learn, we load the iris dataset, choose logistic regression as the classifier, and use accuracy score to measure performance. We also use stratified cross-validation to keep class proportions consistent across folds, along with cross-validated prediction, so each data point is predicted by a model that was not trained on it. We load the iris dataset using Scikit-Learn's load_iris function. This classic classification dataset provides flower measurements as input features and species labels as targets, giving us the basic data needed for a machine learning task. Before training, confirm that the feature data and labels have the same number of entries, so every feature set has a matching label. If the counts differ, raise an error to prevent misaligned data from affecting model training and evaluation. We create 5 stratified folds so each split keeps the dataset's overall class balance, with shuffling and a fixed random state for reproducible results. Then, we set up a logistic regression model with enough iterations to help it converge and the same fixed randomness for consistency across runs. Cross-validation is used to make predictions only for samples left out of training, giving a fair test of the logistic regression model. The cross-validation prediction function creates these held-out predictions across all folds, and the accuracy score then compares them with the true labels to measure overall predictive performance. A Pandas data frame is used to preview the first 5 iris samples by comparing their actual species names with the species predicted through cross-validation. This makes it easy to check how the model performed on samples it did not train on. The output reports the Scikit-Learn version for reproducibility, then shows the model's cross-validated accuracy to summarize performance across folds. It also previews the first 5 held-out predictions alongside their true labels in a clean format. The key point is that each prediction comes from a model that was not trained on that sample, making the evaluation fair. This script uses the iris dataset to show cross-validated prediction with stratified five-fold validation, keeping class balance in each fold. A logistic regression model is trained on each training split and predicts only the held-out samples, so every prediction comes from a model that has not seen that sample. The results include the Scikit-Learn version, the overall accuracy, and a short comparison of the first few predictions with their true labels. Common CV splitters: KFold, StratifiedKFold. KFold cross-validation evaluates a model by splitting the data into several equal folds, then training and validating it multiple times with a different fold held out each time. This lets every data point be used for validation once, which is useful when the dataset is too small for a fixed test set. It gives a more reliable view of model performance than depending on a single train test split. KFold cross-validation is suitable for regression and balance classification, but it can give unreliable results when a class is rare. StratifiedKFold addresses this by keeping the same class proportions in each fold as in the full dataset. This makes it a better choice for imbalance classification because performance estimates are more consistent across folds. Choose KFold for continuous prediction targets, where class balance is not relevant, and StratifiedKFold for categorical targets, where each fold should preserve class proportions. Neither approach is designed for groups data or time-based sequences, so those cases need specialized splitters. Used appropriately, both methods help evaluate models on independent data splits. Python code: KFold, StratifiedKFold. Ordinary and stratified cross-validation folds can differ in how well they preserve class balance. For classification tasks, balanced validation splits are important because uneven class proportions can distort performance estimates. Stratified folds make the class proportions clearer and more consistent across folds. We import NumPy for efficient numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the classification dataset generator to create synthetic data with features such as sample size and class imbalance. We also import standard KFold cross-validation, which rotates validation sets across folds, and StratifiedKFold, which preserves class proportions in each fold. Together, these tools support building and evaluating classification models, especially when class balance matters. We create a small classification dataset with 60 samples and 4 features using Scikit-Learn's Make Classification function. 2 features are informative, while the other 2 add no useful signal. The classes are intentionally imbalanced, with most samples in one class, so we can test how cross-validation methods handle uneven class distributions. A fixed random state makes the results reproducible. Count the labels in the target data using NumPy's bin count function. Then verify that exactly 2 classes are present and that neither class is empty. If this check fails, raise an error stating that 2 non-empty classes are required. This ensures the dataset is valid for classification tasks that depend on both classes being represented. Cross-validation can be set up with 5 folds using shuffling and a fixed random state, so results are reproducible. A standard KFold split randomly divides the data into 5 parts for validation. A stratified KFold split does the same, but also preserves the overall class distribution in each fold, which is especially important for imbalanced datasets. This function summarizes how balanced each validation fold is by calculating the percentage of positive class examples in it. For each split from a given splitter, it looks at the validation targets, finds the average positive rate, converts it to a percentage, and rounds it to 1 decimal place. It then returns the splitter name along with a list of percentages for all validation folds. The code first reports the Scikit-Learn version to support reproducibility, It then summarizes the dataset's class balance by calculating the overall percentage of positive cases. Finally, it compares standard KFold cross-validation with StratifiedKFold by showing the positive class percentage in each fold, highlighting that StratifiedKFold better preserves the original class distribution. This script compares ordinary KFold cross-validation with StratifiedKFold on a small imbalanced classification dataset. Ordinary KFold can create folds with uneven class proportions, while StratifiedKFold keeps the positive class percentage closer to the overall dataset in each split. The output shows these percentages across 5 folds, demonstrating why stratified cross-validation is usually better for imbalanced data. Repeated cross-validation. Repeated cross-validation gives a more stable estimate of model performance by running cross-validation several times with different random splits of the data. By averaging results across these repetitions, it reduces the influence of any one train test partition. This is especially helpful for small or uneven datasets, where a single split could make the results misleading. Repeated cross-validation helps show not only a model's average performance, but also how stable that performance is across different data splits. This can reveal when two models with similar accuracy differ in reliability. It is especially useful when dependable results matter, such as in manufacturing or real estate, or when there is not enough data to set aside a large test set. Choose repeated cross-validation based on the structure of your data. Use RepeatedKFold for independent regression data, and repeated stratified cross-validation for classification, so class proportions are preserved, especially with rare classes. For grouped or time-ordered data, avoid random reshuffling that can mix related records or leak future information. Instead, use group-aware or time-aware validation methods. Python code, repeated cross-validation. This example shows how repeated stratified validation compares model accuracy across multiple reshuffled folds. Repeating the folds helps reveal how much the scores vary, and the final output summarizes accuracy over all repetitions. We import NumPy for numerical work, Scikit-Learn for machine learning tools, a dataset generator to create synthetic classification data, and logistic regression to build a simple binary classification model. We import key Scikit-Learn tools for building and evaluating a reliable classification workflow. Repeated StratifiedKFold cross-validation keeps class proportions balanced across folds and repeats the process to measure performance variability, while the cross-validation scoring function evaluates how well the model generalizes. We also use a pipeline to apply preprocessing and modeling consistently, including standard scaling to normalize feature values for scale-sensitive models, such as logistic regression. We create a small, imbalanced classification dataset using Scikit-Learn's make classification function. It contains 240 samples with 8 features, where 4 features are informative and the class split is 75% to 25%. A fixed random state is used so the dataset can be reproduced. Before training the model, the code verifies that the feature data and target data have the same number of rows. This ensures each set of features has a matching target value. If they do not match, it raises an error to alert the user and prevent unreliable model fitting. We build a simple machine learning pipeline that first standardizes the features, then trains a logistic regression model. Scaling helps logistic regression work reliably because it is sensitive to feature size. The model uses a fixed random state for reproducibility and enough iterations to support convergence, so cross-validation applies the same preprocessing and model setup in every fold. We use repeated stratified cross-validation to evaluate the model more reliably. The data is split into 3 validation folds, and the process is repeated 4 times to capture performance variability. A fixed random seed of 42 makes the results reproducible. We use cross-validation to measure the model's accuracy across different data splits. The cross-validation score function evaluates the model using the features, target values, and a chosen splitter for training and testing folds. With accuracy as the scoring method, it returns 1 score for each fold, helping show how consistently the model performs. Use NumPy to summarize the validation accuracy scores by finding their mean and standard deviation. The mean shows the model's average performance across folds, while the standard deviation shows how much the scores vary. Rounding the scores to 3 decimal places makes the results easier to read and interpret. The output reports key cross-validation results for the model. It shows the Scikit-Learn version for reproducibility, the number of validation folds tested, and the accuracy for each fold rounded to 3 decimals. It then summarizes performance with the mean accuracy and the standard deviation, which indicates how much the results vary across folds. This script evaluates logistic regression on a synthetic imbalanced dataset using repeated stratified cross-validation. It uses standard scaling within a pipeline so each fold is processed consistently, then runs 3 folds repeated 4 times to measure performance across different splits. The output includes the Scikit-Learn version, the number of folds, each accuracy score, and the mean and standard deviation, showing both average accuracy and variability. ShuffleSplit. ShuffleSplit is a cross-validation method that repeatedly creates random training and test sets. Unlike KFold, its splits are not fixed, so a data point may appear in several test sets or in none. It lets you choose both the number of splits and the test set size, making it useful when one train test split is too unstable or KFold is not a good fit. ShuffleSplit works well for regression or prediction tasks when data points are independent and order does not matter. It is less suitable for classification with imbalanced classes because it may not preserve class balance, so a stratified splitter is usually better. It also should not be used when related records must stay together, since similar items in both training and test sets can make results look too optimistic. In that case, use a grouped splitter. ShuffleSplit uses independent random splits to estimate how model performance varies across different training and test partitions. It is useful for large datasets and for checking sensitivity to the choice of training examples, as long as observations are independent. It should not be used for time-ordered data, because shuffling can leak future information into past predictions. Python code, ShuffleSplit. This section demonstrates ShuffleSplit on independent regression data to compare repeated random holdout test sets. It highlights that different splits can share some of the same test rows, and that model scores may vary across these repeated evaluations. We import key tools for a simple regression workflow: NumPy for numerical operations and Scikit-Learn for machine learning. From Scikit-Learn, we use a dataset generator to create synthetic regression data, a linear regression model to fit it, and ShuffleSplit to make random train test splits. We also use cross-validation scoring to evaluate how well the model performs. We create a small regression dataset with Scikit-Learn's makeRegression function, using 30 samples and 3 features. Adding 12 units of noise makes the data more realistic, while setting the random state to 42 keeps the results the same each time. This makes the dataset useful for consistent model testing and comparison. Before splitting the data, the code verifies that the feature data and target data have the same number of rows. This ensures each set of features has a matching target value. If they do not match, it raises an error to prevent problems during model training and evaluation. A ShuffleSplit setup creates 5 random train test partitions, each using 20% of the data for testing. A fixed random seed makes the splits reproducible. A linear regression model is then trained and tested on each split to evaluate its performance across different random divisions of the data. The code uses cross-validation to estimate how well a linear regression model performs on different random splits of the data. A shuffle-based splitter creates the training and test partitions, and the model is evaluated with the R-squared score. This helps show how consistent and reliable the model is across multiple data splits. To examine which rows appear in each test set, we collect the test row indices from every split produced by the splitter. For each split, we ignore the training indices and keep the test indices, sort them, and store them for later review. This makes it easier to analyze how test rows are distributed across the different splits. Create a zero-filled counter with 1 entry for each row in the feature dataset. Then, for each split, use the test row indices to increase the matching counter entries. The result shows how many times each row was included in a test set across all splits. This section checks the Scikit-Learn version, then summarizes how ShuffleSplit creates 5 random train test splits with 20% of the data used for testing each time. It shows which rows appear in the first 2 test sets, then counts how many rows are tested more than once and how many are never tested. Finally, it reports the R-squared score for each split and the average score across all splits to estimate overall model performance. This script shows how ShuffleSplit cross-validation works on a small regression dataset. It creates 5 random train test splits, uses linear regression to score each split with R-squared, and reports the average performance. It also tracks which rows appear in the test sets, showing that some rows may be tested more than once, while others may not be tested at all. This demonstrates both the usefulness and randomness of ShuffleSplit in model validation. Special splitters. Leave out cross-validation tests a model by holding back a small part of the data and training on the rest. In leave one out cross-validation, each observation is tested once, while all other observations are used for training. This is useful for small datasets where every data point matters, and it helps analysts see how well the model predicts individual cases and where errors occur. Inspecting fold assignments in leave out cross-validation shows both its value and its cost. Because each training set is nearly the full dataset, the fitted models are usually similar, and the performance estimate reflects training with almost all available data. But leave one out cross-validation can require many model fits, making it computationally expensive. Reviewing the held-out predictions also helps reveal patterns, such as which housing prices are consistently difficult to predict. Leave out methods test a model by holding back one or more observations and checking how well it predicts them. They are useful for seeing how sensitive predictions are to small changes in the training data. But overlapping test sets can make errors hard to interpret as independent. The main value is a detailed observation-level view of performance, which helps connect specific cases to prediction errors and investigate them more precisely. Python code. Leave out methods. Leave one out cross-validation tests the model by holding out one sample at a time while training on the rest. Each sample serves once as the test case, and the resulting predictions are matched back to their original rows. This setup imports the main tools needed for a simple regression workflow. NumPy and Pandas handle numerical data and data frames, while Scikit-Learn provides tools to create synthetic regression data, build a linear regression model, and run leave one out cross-validation. Predictions are generated across the validation folds, and mean absolute error is used to measure how far the predictions are from the true values on average. We create a small regression dataset using Scikit-Learn's regression data generator with 8 samples and 2 features for easy inspection. Noise is added to make the data more realistic, and a fixed random state ensures the same dataset is produced each time. The code first verifies that the feature data and target data have the same number of rows. This ensures every feature row has a matching target value, which is required for leave one out cross-validation. If the row counts differ, it raises an error to prevent problems during training and testing. We use leave one out cross-validation to evaluate a simple linear regression model. Each data point is tested once, while the remaining data trains the model, giving a thorough check of performance across the dataset. To inspect the first few leave one out folds, we collect a brief summary of only the first 3 splits. For each fold, we record the fold number, the training set size, and the index of the single held out test sample. This gives a quick way to review how the early fold assignments are structured. We use leave one out cross-validation to generate one linear regression prediction for each data point, training on all other points each time. Then we compare each prediction with its actual target value by taking the absolute difference. These absolute errors show how far each prediction was from the truth and provide a simple measure of prediction accuracy. A pandas data frame is used to summarize the leave one out cross-validation results in a clear format. It includes each sample's row index, the rounded actual target value, the rounded predicted value, and the rounded absolute error between them. This makes it easy to compare predictions with true values and see the error for each data point. The output first reports the Scikit-Learn version to support reproducibility. It then summarizes the first few leave one out cross-validation folds, including training size and the held out row, and confirms that the total number of folds matches the number of samples. Finally, it shows a compact preview of predictions with actual values and absolute errors, then reports the mean absolute error as the overall measure of prediction accuracy. This script shows leave one out cross-validation on a small regression dataset with 8 samples and 2 features. A linear regression model is trained repeatedly, each time holding out one sample for testing and using the rest for training. It checks that the data is consistent, previews a few fold assignments, then reports each prediction, its absolute error, the total number of folds, the Scikit-Learn version, and the mean absolute error. Overall, it demonstrates how the model performs when every sample is tested individually. Group-based splits. Group-based splits are used when rows in a dataset are not independent, such as multiple records from the same patient or customer. They keep all records from each group entirely in either the training set or the validation set, preventing the model from learning group-specific patterns. This gives a more realistic estimate of how well the model will perform on new, unseen groups. When reviewing group-based cross-validation, check both fold sizes and which groups appear in each fold. Because groups can have very different numbers of rows, folds may be uneven, but they better preserve the real structure of the data. The key is to ensure no group is split between training and validation, while watching for problems such as one large group dominating a fold, or rare classes appearing in only a few groups. In classification, group separation can reduce class balance, so validation scores should be interpreted with that trade-off in mind. In group-based cross-validation, predictions should be interpreted in terms of the groups left out during each fold. Each prediction estimates performance on an entirely unseen group, helping test whether the model generalizes to new students, stores, or similar real-world entities. Comparing errors across groups can show whether performance is consistent or whether certain groups are harder to predict. This approach helps prevent data leakage while giving a more realistic view of reliability on new groups. Python code, group-based splits. Use group-based cross-validation to ensure that all samples from the same group stay together in a single fold. Then, evaluate the model by inspecting predictions on the groups that were held out during validation. We import NumPy and Pandas to work with numerical data and data frames, then use Scikit-Learn for machine learning. From Scikit-Learn, we bring in logistic regression, a classification model used to predict binary outcomes from input features. We import 3 Scikit-Learn tools for evaluating a model. GroupKFold creates cross-validation splits that keep all samples from the same group together. Cross-validation prediction generates out-of-sample predictions for each data point, and the accuracy score measures how often those predictions match the true labels. We create a small repeated measures dataset with 6 groups, each observed 3 times. Each observation is assigned a visit number from 1 to 3, so every group has the same visit structure. A simple group-level signal is also added, using a repeated pattern of zeros and ones to represent a basic characteristic of each group. A Pandas data frame is created to simulate visits with group-specific signals. Each row represents one visit, with one column marking the visit order and another holding the signal value for that group. A matching set of target labels is then defined using a simple deterministic pattern, so the labels align with the group signals and support a later demonstration of group-based cross-validation. The code first verifies that the feature data, labels, and group identifiers all have the same number of entries. This ensures every observation is correctly matched with its label and group. If the counts differ, it raises an error to stop processing because the data is not properly aligned. We use group-based cross-validation with 3 splits so that whole groups are kept together during validation. Then we set up a logistic regression model with a fixed random state for reproducible predictions during cross-validation. The code first prints the Scikit-Learn version to confirm the running environment and support compatibility checks. It then prints a table header for tracking cross-validation folds, including the fold number, the validation groups, and any overlap between training and validation groups. This helps verify how group-based data splits are organized. For each fold from the group-based splitter, we compare the groups assigned to training and validation. The validation groups are sorted for easier review, and any groups shared with the training set are identified. Since group-based splitting should keep groups separate, shared groups should normally be absent. Printing the fold number, validation groups, and any overlap helps verify that the folds were created correctly. Cross-validation is used to generate predictions for each data point with a logistic regression model, making sure each prediction comes from data not used in training. The predicted labels are then compared with the true labels using an accuracy measure. This gives the proportion of correct predictions and summarizes how well the model performs across all groups. Create a Pandas data frame that records each group and whether each prediction was correct by comparing predictions with the true labels. Then, group the data by group identifier and average the correctness values to get each group's accuracy. Rounding these results to 2 decimal places makes it easy to compare prediction quality across groups. First, report the model's overall prediction accuracy, rounded to 2 decimal places for readability. Then, show the accuracy for each group in a simple dictionary format. Together, these results give a quick view of both overall performance and how well the model performs across different groups. This script shows how group-based cross-validation works using Scikit-Learn's GroupKFold method. It trains a logistic regression model while holding out entire groups for validation, which prevents data from the same group appearing in both training and validation sets. The script reports which groups are tested in each fold, makes predictions for unseen groups, and calculates overall accuracy. It also summarizes accuracy by group, helping you check whether performance is consistent across different parts of the dataset. Time series splits. Time series splitting is used when data order matters because it trains models on earlier observations and tests them on later ones. This avoids mixing past and future data, which can create look-ahead bias and unrealistic performance. It is especially important for forecasting tasks like electricity demand or stock prices, where validation should reflect how the model will be used in the future. In time series cross-validation, an expanding window trains the model on an initial time period, tests on the next period, then grows the training data for later tests. This matches forecasting situations where new data becomes available over time. Checking the fold assignments confirms that training windows expand properly and test windows move forward without overlap, so the validation setup reflects real decision-making needs. In time series cross-validation, predictions must be checked against the actual outcomes from the same future periods, because timing affects how results should be interpreted. A single summary score can hide problems, such as weaker performance during holidays, economic shifts, longer forecast horizons, or certain seasons. Reviewing results fold by fold helps ensure the evaluation reflects the time-ordered nature of the data. Python code, time series splits. Use time series cross-validation to evaluate models while keeping observations in chronological order. This prevents future data from leaking into training. Review each fold and the outer-fold predictions to confirm the splits and results are behaving as expected. We import key Python libraries for data handling, visualization, regression modeling, and evaluation. NumPy, Pandas, and Matplotlib support data work and plotting, while Scikit-Learn provides linear regression, mean absolute error, and time series cross-validation. Time series splitting is used so model validation respects the order of the data. The dataset uses months 1 through 24 as the time sequence. Demand is modeled with a base level of 100, a steady increase of 2 units per month, and a repeating yearly seasonal pattern based on a sine wave. Together, these parts create a simple demand model that trends upward over time while fluctuating seasonally. To predict this month's demand from last month's data, the demand series is shifted by 1 month. Earlier demand values become the inputs, and the following month's demand values become the targets. The matching months are taken from the second month onward, so each input is correctly aligned with the demand it is meant to predict. Before training, confirm that the feature data and target data have the same number of rows. This ensures every input has a matching target value, which is essential for supervised learning. If they do not match, raise an error to prevent misaligned data from causing incorrect training or predictions. We set up time series cross-validation with 4 splits and a test window of 3 periods, so training always uses earlier data and testing uses later data. A linear regression model is prepared for fitting and prediction. We also create a placeholder array to store predictions for the test periods, and an empty record of each fold's training and test months, making the validation process organized and easy to evaluate. For each time series fold, the model is trained on earlier data and then used to predict the following test period. The predictions are saved in their matching positions, and each fold's time range is recorded, including the last training month and the first and last testing months. This keeps the evaluation aligned with time order and makes it clear which periods each fold covers. We summarize the timing of each time series cross-validation fold in a Pandas data frame. It uses the collected fold details, including the fold number, the final training month, and the first and last test months. Clear column labels make it easy to review the sequence of folds without printing large arrays. We first find the months that have predictions by checking which prediction values are not missing. Then we compare actual demand with predicted demand only for those months and compute the mean absolute error. This produces one summary measure of how accurate the out-of-fold predictions are. The code reports the scikit-learn version for reproducibility, then confirms that each time series test block follows directly after its training block to preserve chronological order. It summarizes the timing of each fold by showing the training end month and the test period, then reports the mean absolute error for the out-of-fold predictions as a measure of model accuracy. This plot compares actual monthly demand with cross-validated predictions while preserving chronological order. It uses a clear figure with separate markers for the observed values and predicted values, labels the month and demand axes, and includes a legend to distinguish the two series. The final display provides a concise visual check of how well the time-aware predictions match the actual demand. This script shows how to use time series cross-validation on monthly demand data. A linear regression model predicts each month's demand from the previous month, while each fold trains only on earlier months and tests on later ones to avoid future leakage. It records out-of-fold predictions, reports the train and test periods with a mean absolute error, and compares actual demand with predictions in chronological order. In this lecture, you learn to use Scikit-Learn cross-validation utilities to estimate model performance, choose appropriate splitters for classification, regression, grouped, and time-ordered data, and inspect fold assignments and predictions produced by cross-validation. In the next lecture, Lecture B, we will go over evaluation design.
Thank you for your attention. See you all in the next lecture.